So let's look at A1E. This is on, what page? This is on page 86 in your textbook. So it says to compute the following products in S9, and the products that we're looking at is going to be 147 and 1678. 74132. So I'm just going to actually write it as a full permutation. They say in S9, that means that we're going to have 9 columns that we need. And the first column, the first row is just the numbers 1 through 9. Now let's look at our transposition here. These go from left to right. So we're looking for 1 in the first one over here. 1 goes to where? 3. You have 1 here on the right. The number after it is 3, so it's saying 1 gets matched to 3. Then we go to the next one over here. It doesn't have a 3 in it. No. So that just leaves 3 at 3. Then we go to the last one. Does it have a 3 in it? No. So it leaves 3 at 3. So 1 gets mapped to 3. Now, look at the next one. 2. Where does 2 first appear? In the very last one. So it goes all the way back to the very first number. So 2 goes to 7. Go over 1. Does 7 go anywhere? To 8. Go over 1. 8 doesn't go anywhere. So 2 goes to 8. So tell me about 3. In that first one, 3 goes to 2. Go to the next one. Nothing. Nothing. So 3 goes to 2. So you tell me about 4. 4 goes to 1. 6. Stop. So 4 goes to 6.
So
You guys figuring this out a little now?
yeah.
It's beautiful, but
Yeah, it's painful.
So like you start at the back end.
Yeah, you always, function composition works from,
Oh yeah.
backwards. And these are function composition. So let's look at, 5. Tell me about 5. 5 goes to 5. It's not there anyplace. Tell me about 6. 6 goes to 7. 7 goes to 1. So 6 goes to 1. Tell me about 7. 7 goes to 4. 4 goes to 7, so 7 goes to 7. Tell me about 8. 8 goes to 1. 1 goes to 4. And no 9, so 9 goes to 9. That's how you do products of cycles. It's starting to make sense? Yeah, if you don't understand products of cycles, this entire section is lost. Okay, so then let's look at A2A. So that was A1E, A2A. This one says, write each of the following permutations in S9 as a product of disjoint cycles. So let me go ahead and write the permutation here. Uh, 492. 517. 683. So we have to write this as a product of disjoint cycles. So this actually isn't, let's move this up. There we go. Our solution then is going to be, I just like to start with the first one. Remember, you're just writing them. Where you start with is the first number you're going to put down. So I'm going to write 1 down here. 1 is where we start. And then where does 1 go in this permutation? 1 goes to 4, so we put that down next. Where does 4 go? 5. So we put that down. Where does 5 go? 1. We don't put that down, but that cycle is done because we ended back up at the beginning. Now let's start with the first number that wasn't in the first cycle. So that's going to be 2. Where did 2 go? To 9. Where does 9 go? Where does 3 go? To 2. Do we put 2 down? No. Now, start with the first one you don't have. We have 1, 2, 3, 4, 5. So the next one would be 6. So where does 6 go? 7. Where does 7 go? 6. So we don't write it down. And then 8 is the next one, but 8 goes to where? Itself. So we don't put it down at all. And then 9 we have covered, so we're done. That makes sense? Yeah, 9's taken care of. So we don't have to worry about that. Question?
How did they get repeats in the one we just did? As compared, well, the one we just did, we didn't have any repeats, but above there was
Above.
one.
There's more than one way to write the cycles down. What I showed you was writing them as disjoint cycles. You can write things down in more than one way, but you'll notice that when they have the repeats, we have some things that 7 went to 4,
Yeah.
and then it went back to 7. So that was a way of writing 7 to 7. So there's an infinite number of different ways of writing these, because you can add those identities in, as many of them as you want. I'm only teaching you how to decompose them into disjoint cycles. The other ones are guess and check. There's no real method to it. Yeah. Any other questions on that? Okay, what we need to do, I want you to work on A1 and 2 right now, and after you get a really good feel for this, we're going to jump into transpositions probably in about 15 minutes. So go ahead and work on those first two numbers, A1 and 2, the homework problems that you have from those sections from Part A. Try and do all of those sections from Part A. And, oh wait, let's skip number 4, 5 and 4 in the reverse order. I wanted to do A3, A2. Let's look at A3A. We want to get all of Part A done so you guys can do that. Express each of the following as a product of transpositions. So, number A, 137, 428. So there's the cycle. And there's more than one way to represent these as a product of transpositions. But when you're writing transpositions, if you look at the pattern, turn back with me to the pattern they use, and I'm just going to show you this pattern. It's on the bottom of page 83. Notice that the pattern that they give on the bottom of page 83 for the it's about the third equation up from the bottom. They take the last number and then they group it with each of the previous ones in order. So if I want to group this one, I would take my last number of an 8 and group it with each of the previous ones. So that would be 8 grouped with 2, then 8 with the one before 2, which is a 4, and then 8 with a 7, 8 with a 3, I can barely read that screen anymore, and 8 with a 1. Now, how does this work as transpositions? How would, if we were just trying to figure out where this gets mapped to, tell me, looking at this, choose 1, where does that go? 1 goes to 8. Now you go over 1. 8 goes to 3. 3 doesn't appear anywhere else, so you're right here. 1 indeed went to 3. That makes sense? Now let's see where 3 goes to. So we come over here, we find 3. 3 goes to what? 8. Then 8 goes to where? 7. No 7's here. Notice 3 goes to 7. So look and see where 7 goes. Find 7 is right here. 7 goes to 8. 8 goes to 4. 7 goes to 4.
But when you did the first one, like when you stopped, did you like start new parentheses?
No, I don't know what you're saying. This one I'm doing a transposition. I'm not doing disjoint cycles. These aren't disjoint cycles. These are transpositions. So they are not in any wise disjoint, but they give you the same answer as this cycle over here, which is a disjoint cycle. Yeah, I can. Is that good or more?
So the solution we just did, this whole 8 2 8 4 8 7, is that just a basic way to get the cycles down?
Yes, this is how you get your cycles down, but this 8 2 8 4 8 7 8 3 1, this isn't cycles, these are transpositions. Transpositions are cycles of length 2, and they're usually not disjoint. Remember, transposition simply means a cycle of length 2. That was our definition. How do you write a disjoint cycle as a cycle of length 2? There's an infinite, as a set of transpositions, there's an infinite number of ways of doing it. It's not unique, but this is one method that works. And the method is simply take the last number and group it with each of the previous numbers in sets of 2. In that order. Okay? So there's more than one way to do that, but that is a method that works. That's the method this book introduces. Okay. We are going to come back to finding inverses and talking about the theorem 2, or is it theorem 1, that big old long theorem that they proved. We're going to do that in a minute, but I want you to feel more comfortable with cycles and transpositions. So I want you to do your homework for part A. So go ahead and get in your groups and do that homework for part A, and then we'll go back and talk about the proofs in that section.
So the A3, that's, or A3, that is...
Yeah. I think number 4, part of number 1. You have to find inverses. So if they tell you alpha is equal to some cycle, 3714 is the one I was using, to find the inverse, what I did is I wrote down what that cycle would be for the full set. And notice that the only things that go anywhere are 3, 7, 1, and 4. Everything else stays the same. So 2, 5, and 6 stay the same. And I wrote down what 3, 7, 1, and 4 go to here. And then I calculated the inverse, and we learned how to do that last time. So after you get the inverse, then you calculate your cycle for it. Just like how we've done it. It's not exactly backwards, because this is 1734. Backwards would be like 4173, something like that. You can't change the order inside your cycle. Because if you change the order, if you made this 7, 3, 4, 1,
What could you make it 7, 1, 4, 3?
yeah, you can take the. Say that again? You're saying if you made this 7, 1, 4, 3.
7, 1, 4, 3, is that the same as 3, 7, 1, 4?
Yeah, you can move the 3 to the end, but it doesn't matter.
Okay, so, and then can you move this out the answer to the other side, so you do 1, 4, 3, 7?
You have to do it in order. So if you have 3, 7, 1, 4, you can write it 7, 1, 4, 3, and then you could have 1, 4, 3, 7. But you have to do it one at a time, otherwise you're changing your order.
Okay, so
What you can't do is you can't just invert 2 of them.
if we do it one more time and then do it backwards, isn't that the same answer as the inverse?
Then you say do it backwards, 3, 7, 3, 4. Yeah, it eventually ends up being
Are
backwards.
they all in the like that?
See, that's what I thought and saw too.
They should. They should.
It made sense to just put it backwards.
Yeah.
You have to be careful. I'm not going to make that claim without proving it. And have I proved it? No, I haven't proved it. But in just thinking about what an inverse does, it goes from where you were to where you got there from. So it should have something to do with being able to reverse in some form. So yeah, I think it should work. But
It's just that
yeah,
check.
yeah. I have to prove it. We can work and prove it, but we're not going to do something like that. Yeah, I think so. I think that actually works. I never thought to ask that question. It's a good question. I always just wrote down the permutation and read the inverse off from it. So that's how you're finding inverses. Now, what about the inverse of a transposition, and why would I care about the inverse of a transposition? If you were comparing your proofs, before we get to this, let's go look at the second proof in the book. The second proof in the book had 4 cases on it. Let's look at those four cases first of all, and then we'll look at these proofs of the inverses. So tell me about the 4 cases. What was the first case? Where you have what?
TK equals X, or, yeah.
TK. TK minus 1 or?
Yes, TK minus 1.
Oh. TK minus 1. I'm going to make this bigger. I cannot see it that small.
Times TK equals.
Yeah, now I can see it. TK minus 1 times TK.
Equals XA.
Okay, so we had the repeated one. What happens in this one? Let's evaluate this. Let's start with A. A is going to go to X in the first one, right? And then X goes to where? A. So A goes to itself. And where would X go in the first one? X goes to A, which goes to X. So what transposition, what cycle is this? A and X all by itself because they go to themselves. This is your identity cycle. It takes A to A, it takes X to X. Does that make sense?
I thought we didn't do that.
Well, I didn't write them individual. I just wrote it so you guys could see it. I'm getting ready to erase it.
That makes sense.
It's kind of scratch.
So,
A goes to
That would be
A.
helpful if it was there, they don't put it there.
You don't put it there because inside a proof, you don't have it there, but this is just scratch work. So you can think of these as the single cycles. A goes to A, X goes to X.
But does
Because A goes to X and then X goes to A. X goes to A goes to X.
okay, because I was so confused in this proof.
Yeah, that's why we're going through it. So that gives you the identity. So they are going to take those 2 cycles, those 2 transpositions, and replace them with the identity, which means they can write the transposition as a transposition with 2 less cycles in it. Does that make sense? They reduce it by 2. So this is a case where they reduce by 2. Yeah, because you replace TK minus 1 and TK by epsilon, which essentially goes away. You don't have to put it there. So you're crossing off 2 of them. You don't need it. Let's look at the second case.
Which is TK minus 1 equals XB.
Yeah, let's see. Where's my... Let's copy and paste. Equals what?
It's only TK minus 1 equals XB.
Yeah, but then you times
Yeah.
Yes, but then you
And but,
multiply it.
but then by TK, and TK was XA, right?
Yeah.
Yeah. So let's multiply this together and see what we get. Where would A go? And let's write it as
To B.
1, 2, 3. Yeah. Then we're going to have 2 rows and 3 columns. So we're going to have A, B, and X. So where does A go?
To B.
To X and then
Or
to
to
B.
X.
Yeah. Goes to B. And where does B go? To X. And where does X go? To A. Now notice that they write down something else here.
B
They-
not equal.
They give on the second line another product to check. What is the set of transpositions on the second line?
XB, or AB.
Yeah,
I don't have my book. Does someone
It's
have that book?
XB times XA equals XA times AB.
Yeah, XA times AB. That's what we want to check. So XA times AB. Now, let's calculate that one. Same type of idea.
How would we know to do that?
You always verify whenever they make claims of equality in proofs. You always just plug it in and verify. You always check it.
Is that why? Why is it AB instead of?
What their goal is that they want to be able to write a transposition where X is farther to the left than in the first one. So this one is just moving. So if they replace XB and XA by XA and AB, now in the second one they don't have any X's. So then by 1 they have moved X to the left. And we're actually going to do continuing. It has to stop after some finite time because you only have so many length for your transposition, and then you run out of places to move it to the left. So you have to be done. So that's where we're going to get an argument in the proof. But let's check this. Where does A go? A goes to B. Where does B go? To X. And where does X go? To A. Is that the same? Yeah, so we have two equal ones. So when you're reading this proof, you would actually go through that process and verify that those two are equal. You evaluate it. So this is where we're going to replace this value right here with this value, and it's going to be XA and AB. So that was the second case. Let's look at the third case. In this case, we have CA and XA. CA and XA. So calculate this. What do we think it's going to be? Where does A go? A goes to X. Where does B go? Oh, we need a C. Where does C go? And where does X go?
C.
To C. And then the next one that we have, the second one that they're going to replace it with is XC and CA. So let's calculate this one. This is going to be our C, and we'll replace this. Where did it go? Oh, right there, sure enough. Moves around, confuses me. So A goes to, A goes to C, C goes to X, that's correct. And then C goes to A, and X goes to C. Are they the same? And so then we can replace our original here with something that moves it one place to the left. And this would be XC and CA. So now we don't have any x's in that right-hand one, we have moved it to the left-hand one. And then we have one more case to look at. And in case 4, we have BC and XA. So, calculate this one. So, A, B, C, X. Actually, this one's easier. We don't need the whole, well, we'll put it in here. Insert a column. Yeah, so A goes to what? B goes to C. X goes to, and C goes to B. What's happening with this one? Could I write this? Maybe I'll, yeah, notice what they did on this one. They just switched the order. Does that give us the same thing? Yeah, it doesn't change it. You can verify that, but it's going to be the same thing. So, we're going to replace the TK minus 1 and the TK with the second one. With the XA and the BC. And here again, that moves the X one place to the left. And now, if you look at the last part of the proof, it said continuing in this fashion, what happens? Continuing in this fashion, you're going to have one of those 4 cases happen. That's your only possibilities. We've exhausted all the possibilities. So one of those 4 cases has to happen. In the first one, you've reduced it by 2, so you're getting a shorter transposition. In cases 2, 3, and 4, you're moving X 1 point to the left. So eventually, X moves to the first transposition, or you only have 1 transposition left. Do you see what's happening? So continuing in this fashion, we see that either X is in the first transposition, or we have 1 transposition left. Otherwise, if we had more than 1 transposition left and X wasn't in the first position, we'd redo it again. And you'd either drop 2 transpositions or you'd move X1 over and repeat it again until one of these 2 cases happens. Well, tell me what happens if you have the first case, if X is in the first transposition. What did your proof there conclude in that last paragraph? What did it say happens in that last paragraph? Why are you done? Why are we done?
So it's impossible.
Why is it impossible? Yeah, it says for if T1 equals to XA and X doesn't appear after that, then what happens when you look at the identity on X? Yeah, it has to be equal to A. That means the identity operation is taking X to A because it's not taking it anyplace else. In other words, but you guys have blank looks. Let's look at a transposition. So here's transpositions. Tell me where it's taking 2 to. 2 goes to 1. And 1 goes to 2. But remember, this was equal to the identity transposition. So it was equal to, say, 2, 1, and then something else. The only places where the 1 exists, for instance, that's our x. This is going to be our x. Is right here. So if you did the operation on x, it takes it to the other number that you have there. It doesn't take it back to itself. Because epsilon is all your transpositions put together. This number doesn't appear in anything after it. It's getting mapped to something not itself. So it means it's not the identity. Okay? If x is only in the first transposition, then epsilon of x, which is equal to the product of the transpositions, is equal to whatever our xa was times a whole bunch of different things. You know, where this is just notes here. This epsilon, not epsilon of x, our epsilon transposition is going to be equal to that, and that tells you epsilon of x is not equal to x. A contradiction. So we verified that contradiction. If we have just one transposition left at the end, what problem do we have? Can't be an identity. If you just have one transposition, if you have 2, 1, then epsilon of 2 is equal to 1. Epsilon of 1 equals to 2. It's not the identity. An identity has to have more than one transposition to get back to the original element. Okay? It'll take x to something not x. Therein is your proof to that theorem. Yeah. It's an argument, lists all the possibilities, and kind of, you guys remember from history of math where the reductio ad absurdum, you keep reducing it, you keep repeating it, but you don't have an infinite number of ways of repeating it, something fails. That's exactly what's happening here. You're repeating it so many times that you're going to get one of these cases in the end, which gives you the problem. So that was based on the assumption that epsilon was an odd number of transpositions. So to fix it, your conclusion is your identity has to be an even number of transpositions. Identity is an even number of transpositions. Therein makes the next proof easy. If you understand one thing from the next proof, and here is what you need to understand. If you're looking at function composition, and you want to take inverses, because they start the next proof off by saying, consider pi and pi inverse. Pi is any transposition. What is the inverse of a transposition? Put on the brace and go, I don't know. What is the inverse of a transposition? Well, if you have function composition and you're doing the inverse of function composition, it is just going to be switch the order and take the inverse of each one. Switch the order, take the inverse of each one. So if you have a transposition and they're just functions, if you want to take the inverse of them, switch the order and take the inverse each one. So look at up here. 5, 4, 5, 3, 5, 2, 5, 1. So you can change the order, take the very last one right at first, then each of them so forth. And then inside, I switch the order of each one. In a transposition, that is not completely necessary. But in your cycles, I think that's what's going to happen, is switching the order. I didn't actually prove it for cycles, I only did it for transpositions. But you can switch the order inside each one, and that gives you the inverse, because it changes the order of the function composition. That's how you find an inverse for function composition. So if you have pi is this transposition,
pi inverse is going to be this one. How many products of transpositions do you have for each of those? How many products do I have on the one list up there at number 7? 4 of them, right? How many do I have in the inverse? 4 of them. Pi and its inverse can be represented using the same number of transpositions. That is what the proof of theorem, that last theorem hinges on. Pi and its inverse can be represented using the same number of transpositions. So if pi has an odd number of transpositions, you can represent its inverse doing exactly what I did there with an odd number of transpositions. If pi has an even number of transpositions, you can represent its inverse just the same way as I did it right there with an even number of transpositions. They're going to have the same number of transpositions. Therefore, when you do function composition to get to the identity, you're going to have an even number because an odd plus an odd isn't even. An even plus an even isn't even. And that's what that last proof hinges on. Because they're just doing pi composed with pi inverse to get to your identity, applying theorem 2 to know that you have an even number of transpositions for your identity, to know that you have to split the number of transpositions up between pi and pi inverse to arrive at your conclusions. They're either both even or both odd. Okay? That is that last proof. We are out of time for today. Let me know if you guys have any problems with this. This is brand new information. You guys have likely never seen it before. What? You've seen it before?